Chapter 4. What is time to me? Part A. What is time? Time can be a river, a thread, or a slideshow. It's all about where you're standing and how you choose to see it. Clovis. Time is a unifying force. It is a deeply complex and multifaceted concept that plays a crucial role in our understanding of the universe. From the absolute time of Newtonian mechanics to the relative time of Einstein's theories, and from philosophical debates about the nature of temporal reality to subjective experiences of time's passage, our understanding of time is vast. Here is an overview of what time is, according to different perspectives. Physics, classical mechanics, Newtonian time. In classical mechanics, time is considered absolute and universal, flowing uniformly and independently of any observers or events. Sir Isaac Newton described time as absolute, true, and mathematical. Time, of itself and from its own nature, flows equably without relation to anything external. Relativity. Einstein's theory of relativity. Albert Einstein revolutionized our understanding of time with his theories of special and general relativity. In special relativity, time is relative and can vary for different observers depending on their velocity. This leads to phenomena such as time dilation, where time slows down for objects moving at high speeds relative to an observer. Space-time. In general relativity, time is intertwined with space to form a four-dimensional continuum known as space-time. Massive objects like stars and planets warp space-time, and this curvature affects the passage of time, leading to gravitational time dilation. Quantum mechanics, quantum time. In quantum mechanics, time is treated as a parameter that orders the sequence of events. However, the concept of time at the quantum level is still a topic of ongoing research and debate, particularly in the quest to reconcile quantum mechanics with general relativity into a theory of quantum gravity. Philosophy. Presentism versus eternalism. Presentism. The philosophical view that only the present moment is real and the past and future do not exist in the same way as the present. Eternalism. The belief that past, present, and future events are equally real. This view is sometimes supported by the block universe theory, which posits that time is another dimension like space, and all points in time exist simultaneously. Perception of time. Phenomenology of time. Philosophers like Edmund Husserl and Martin Heidegger have explored how time is experienced subjectively. The phenomenological approach examines how time is perceived and lived by individuals, emphasizing the difference between objective, clock, time, and subjective, lived, time. Psychological time. Time. Perception. Humans perceive time subjectively, and this perception can vary based on factors such as attention, memory, and emotional state. An example that we all experience. Time may seem to pass quickly when one is engaged in enjoyable activities and slowly during boredom or waiting. Metaphysical and speculative views, temporal dimensions, and higher realities. Some theories and speculations extend beyond mainstream physics and philosophy, proposing that time might be influenced by higher dimensions or other forms of reality. These ideas often explore the nature of consciousness, altered states, and the possibility of time travel or temporal manipulation through advanced technologies or spiritual practices. Time is the most valuable resource mankind has, yet we certainly will never have enough of it in our lives. But what if we could? What if we could have all of time? What if time is not what we were taught it was? What if time never moves at all? But instead, our consciousness was moving from time dimension to time dimension. The idea of time being akin to a slideshow or a static sequence of events, with individuals moving through it, is an intriguing concept that has been explored in philosophy, physics, and metaphysics. This notion challenges our intuitive understanding of time as a continuous and flowing phenomenon, and raises questions about the nature of temporal experience and reality. Part B. What is a temporal dimension or time dimension? A temporal dimension or time dimension is a concept that can be understood in various contexts, often depending on the field of study or the theoretical framework in which it is used. Here's a breakdown of the term as it relates to different disciplines. Physics and cosmology. In physics, especially within the context of spacetime in the theory of relativity, time is often considered the fourth dimension, alongside the three spatial dimensions: length, width, and height. Fourth dimension, time is treated as a coordinate in a four-dimensional spacetime continuum. Events are specified by four coordinates: 3 for spatial position and 1 for the time at which the event occurs. Higher dimensions. In theories such as string theory, additional spatial and possibly temporal dimensions are postulated. These are beyond the conventional 4 dimensions and are usually compactified or not directly observable. Philosophy of time. In the philosophy of time, temporal dimensions can be understood through various theories about the nature of time itself. Presentism. Only the present moment is real. Eternalism, past, present, and future events are all equally real, and time is another dimension similar to space. Growing block universe. The past and present are real, but the future is not yet real. The block of time grows as new moments are added. Temporal-Subjection theory, TST. In the context of temporal-subjection theory, TST, a temporal dimension might be conceptualized in a more complex and nuanced way. Nonlinear time. TST suggests that time is not a linear progression, but a multidimensional construct where past, present, and future exist simultaneously. This aligns more with the eternalism view in philosophy. Multiple temporal dimensions. Beyond the traditional single temporal dimension, TST might posit multiple temporal dimensions, allowing for various potential timelines or paths through time. This could involve different experiences or perceptions of time based on consciousness. Time shifting. TST proposes that individuals can shift their consciousness across these different temporal dimensions, experiencing past, present, and future in nonlinear ways. Cognitive science and psychology. In cognitive science and psychology, temporal dimensions can refer to how humans perceive and experience time. Subjective time. The perception of time can vary greatly between individuals and can be influenced by psychological states, attention, and cognitive processes. Temporal illusions. Experiences where the perception of time is distorted, such as during intense focus, time seems to speed up, or boredom, time seems to slow down. Metaphysical and esoteric contexts. In metaphysical or esoteric contexts, temporal dimensions can be associated with broader and more abstract ideas like spiritual time or higher consciousness. Spiritual time. Some belief systems propose that spiritual experiences can transcend ordinary time, experiencing moments or events from the past, future, or alternate realities. Higher consciousness. Advanced states of consciousness might allow individuals to access or perceive multiple temporal dimensions beyond the standard linear experience of time. Combining these perspectives, a temporal dimension in the context of TST can be seen as a framework that 1. Recognizes time as a multi-layered construct, not confined to a single linear progression. 2. Suggests that consciousness can navigate these layers or dimensions, potentially altering one's perception and experience of time. And 3. Incorporates insights from physics, philosophy, psychology, and metaphysics to offer a holistic understanding of time as more than just a sequence of events. Growing block theory is a philosophical perspective on the nature of time that shares similarities with both eternalism and presentism. According to this theory, time is conceptualized as a three-dimensional block that is constantly expanding, or growing as new events occur. Key aspects of growing block theory include past and present reality. Growing block theory maintains that both past and present moments are real and existent, like eternalism. Events that have already occurred are considered part of the fixed past, while present events are actively unfolding. Open future. Unlike eternalism, growing block theory suggests that the future is not pre-existing or fixed. Instead, the future remains open and indeterminate until events unfold and become part of the present, and subsequently, the past. This open-endedness of the future contrasts with the deterministic view often associated with eternalism. Expanding block. Time is conceptualized as a growing or expanding block, where new events continuously add to the existing structure. Time progresses. The block grows larger, incorporating new moments and experiences into the framework of reality. Static past. Similar to eternalism, growing block theory posits that past moments are fixed and unchangeable. Once an event has occurred, it becomes part of the static past and cannot be altered or undone. Growing block theory offers a middle ground between eternalism, which treats all moments in time as equally real, and presentism, which holds that only the present moment is real. It acknowledges the reality of both past and present, while leaving the future open and contingent on the unfolding of events. While growing block theory provides a compelling framework for understanding the nature of time, it also raises philosophical questions about the relationship between past, present, and future, as well as the implications for free will, causality, and the nature of reality. Part C. What is infinity in time and why does it matter? Infinity must be looked at as polar, dual, in order to exist as time. In this sense, negative infinity locks the past subjective memory in place. Time is, and will always be, an illusion to the subjective observer. In the realm of quantum mechanics, time is a fundamental parameter that governs the evolution of quantum systems and the behavior of particles and fields at the quantum level. The experience of time in quantum mechanics is characterized by several key principles and phenomena. Quantum superposition. One of the most intriguing aspects of quantum mechanics is the principle of superposition, which allows quantum particles to exist in multiple states simultaneously until they are observed or measured. In a superposition of states, time plays a crucial role in determining the probabilities associated with different outcomes when a measurement is performed. Unitary evolution. The evolution of quantum systems over time is governed by the Schrödinger equation, which describes the unitary evolution of the system's wave function. This evolution is deterministic and reversible, meaning that the state of the system at any given time can be predicted from its initial conditions using the Schrödinger equation. Quantum measurement problem. The concept of time in quantum mechanics becomes particularly intriguing when considering the process of quantum measurement. According to the Copenhagen interpretation, when a measurement is made on a quantum system, its wave function collapses to one of the possible eigenstates corresponding to the measurement outcome. The exact mechanism by which this collapse occurs, and the role of time in the process, remains a subject of debate and interpretation in quantum theory. Entanglement and non-locality. Quantum entanglement, which occurs when the states of two or more particles become correlated in such a way that the state of one particle depends on the state of another, challenges our classical intuition about the flow of time and locality. The phenomenon of entanglement suggests that quantum systems can exhibit non-local correlations that transcend traditional notions of spatial and temporal separation. Time-energy uncertainty principle. In quantum mechanics, there is a fundamental uncertainty relationship between time and energy, analogous to the Heisenberg uncertainty principle. This time-energy uncertainty principle implies that precise measurements of time and energy cannot be simultaneously known beyond certain limits, leading to intriguing implications for the dynamics of quantum systems. Infinity in time isn't just a concept, it's the backdrop of existence, where past, present, and future coexist in a cosmic dance. Time might be infinite, but what if consciousness is the vessel that navigates this endless expanse, exploring each moment as an uncharted horizon? Clovis. Overall, the experience of time in quantum mechanics is intertwined with the probabilistic nature of quantum phenomena, the unitary evolution of quantum states, and the fundamental principles that govern the behavior of particles and fields at the quantum level. While quantum mechanics provides powerful theoretical frameworks for understanding the dynamics of microscopic systems, the nature of time in the quantum realm continues to be a rich and complex area of exploration in theoretical physics. In the realm of quantum mechanics, time is indeed a fundamental parameter that governs the evolution of quantum systems and the behavior of particles and fields at the quantum level. If time is infinite, it would have several profound implications for quantum mechanics and our understanding of the universe. Quantum systems evolve according to the Schrödinger equation, which describes how the quantum state of a system changes over time. If time is infinite, quantum systems would theoretically evolve forever, leading to infinite quantum trajectories. Each quantum system could have an infinite number of possible trajectories and states over an infinite timeline. This aligns with the idea of the multiverse, where all possible outcomes occur in different branches. Recurrent states. Over infinite time, it's conceivable that quantum systems could revisit previous states. This concept, known as Poincaré recurrence, suggests that given enough time, systems could return to a state arbitrarily close to their initial condition. Quantum entanglement, where particles become interlinked and the state of one instantly influences the state of another, would have unique implications in an infinite timeline. Endless entanglement. Entangled particles could remain correlated across infinite time, potentially leading to a complex web of entanglement that spans the entire universe over infinite epochs. Decoherence over infinite time. Decoherence, the process by which quantum systems lose their quantum behavior and transition to classical states due to interaction with their environment, would play out indefinitely. This continuous process might lead to a state where classical behavior dominates at macroscopic scales, but quantum effects remain significant at microscopic levels. In quantum field theory, the vacuum state is not empty, but filled with fluctuating fields and virtual particles. Over infinite time, persistent quantum fluctuations, the vacuum would continuously experience fluctuations, potentially leading to the spontaneous creation of particles and even new universes in a multiverse framework. Stability and instability. Infinite time could test the stability of the vacuum state. Small instabilities could lead to significant changes over long periods, influencing the large-scale structure of the universe. The many worlds interpretation, MWI, of quantum mechanics posits that all possible outcomes of quantum measurements are realized in separate branching universes. An infinite timeline would enhance this interpretation. Endless branching. Every quantum event would lead to a branching of universes, resulting in an infinitely branching multiverse. Probability distributions. Over infinite time, every possible outcome would occur infinitely many times, making the probability distributions in quantum mechanics reflect the relative frequencies of these occurrences. Quantum computers leverage quantum superposition and entanglement to perform computations that would be infeasible for classical computers. In an infinite timeline, infinite computations, quantum computers could, in theory, perform an infinite number of computations, solving problems that are currently beyond reach. Decoherence challenges. Maintaining coherence over infinite time would be a significant challenge, as environmental interactions would continually cause decoherence. The second law of thermodynamics states that the entropy of a closed system tends to increase over time. In the context of infinite time, quantum systems and entropy, quantum systems would continually evolve towards states of higher entropy. However, quantum mechanics allows for fluctuations that could locally decrease entropy, leading to a complex interplay over infinite time. Heat death and quantum effects. While classical thermodynamics predicts a heat death scenario where the universe reaches maximum entropy, quantum effects and fluctuations might introduce new dynamics, potentially preventing a static end state. Infinite time in quantum mechanics raises several philosophical and interpretative challenges. Determinism versus indeterminism. Infinite time exacerbates the debate between determinism. Every event is determined by preceding events. And indeterminism. Some events are truly random. The existence of infinite time could imply that all possible events will occur, blending determinism with probabilistic outcomes. Concept of now. The concept of the present moment becomes complex in an infinite timeline, as the distinction between past, present, and future might blur at the quantum level. The idea of infinite time introduces fascinating and complex dimensions to quantum mechanics. It challenges our understanding of quantum evolution, entanglement, decoherence, and the nature of reality itself. Infinite time suggests a universe of boundless possibilities, where quantum systems evolve eternally, leading to a richer and more intricate tapestry of existence than we can currently comprehend. Part D. Temporal wave functions. Building on the idea of wave functions in quantum mechanics, we can propose that time itself might have a wave function-like description. This temporal wave function would represent the probabilities of different temporal states or experiences, analogous to how a particle's wave function represents its possible states. For example, just as a particle's wave function can describe a superposition of states A and B, a temporal wave function could describe a superposition of different temporal experiences, such as past, present, and future. This concept suggests that our experience of time is not fixed, but can be influenced by our interaction with these fundamental quantum states. With this new understanding, we need to look at time differently. Time as a static event would mean we are the ones moving through it. Picture a cartoon flipbook again, with a drawing of a man walking toward two doors. As the pages flip, the man approaches the door. The whole flipbook is time, and in order to move the man, the conscious experience has to move. Each new flip is a new temporal dimension. In the context of physics, including Einstein's theory of relativity, space-time is considered a unified entity comprising three spatial dimensions: length, width, height, and one temporal dimension, time. Together, these four dimensions constitute the fabric of the universe in which events occur and objects move. The temporal dimension, specifically, represents the aspect of reality associated with the passage of time. It allows us to order events, perceive change, and understand the concept of past, present, and future. In physics, time is treated as a dimension akin to space, and it is integrated into the mathematical framework of space-time. In theoretical physics, especially in discussions about higher dimensional models or cosmological theories, the concept of additional temporal dimensions beyond the familiar linear progression of time in our everyday experience is occasionally considered. These concepts are speculative and often explored in the context of multidimensional theories like string theory and brain cosmology. As we walk toward the doors, it is our consciousness experiencing the movement from one time dimension to the next. Time dimension in the flipbook. In the infinity of time, there are infinity time dimensions, infinite choices, infinite possibilities, and infinite outcomes. When time is viewed as a reality of infinite, the future is now infinite. The flips progress. Which door will you walk towards? One is on the left, and one is on the right. In the reality of infinite, you have already chosen. You have made every possible choice in the reality of infinite. You chose left, and you chose right. But it goes farther, because you also chose not to choose. And you chose to walk away. And you chose, well, everything. Because we live in a reality, this reality must be able to create infinite paths through time. Every path in time must exist in the reality of infinite. The unifier here is you. Your conscious experience helps reality to dictate the choices we have. The infinite time dimensions allow us a unique opportunity to help shape our reality. The wave phenomenon of particles allows reality to be, well, malleable. As we focus on what door to choose, that reality, that time dimension, happens at the speed of light. And we perceive it as one solid reality, but it is just the next page in the flipbook. In the multiverse of infinite, it is time dimensions that are infinite, while your consciousness is experiencing them all, but perceiving just the one you choose. Time dimensions run on an axis parallel to our conscious focal plane. When our consciousness lens perceives time dimensions, it filters them down until one or more crosses through our conscious focal plane, allowing the perception of time passing, while simultaneously creating the holographic reality that we experience. If time is infinite, then every quantum system has an eternal story to tell, an endless sequence of moments, possibilities, and outcomes waiting to be realized. Within an infinite timeline, quantum states don't just evolve. They circle back, replay, and explore every path, as if the universe itself were a tireless traveler on an eternal journey. Clovis. Focusing on diverging your consciousness lens can shift your perceived conscious focal plane, allowing access to infinite time dimensions. While this can have profound effects on our individual perceptions, it comes with profound ethical, moral, spiritual, and philosophical risks. Caution. This could lead to unintended time alterations outside of our control due to shifts in time dimensions. Simply put, I want money, and I focus on money while shifting time. Then, the next day, I get a call that my parents passed away, leaving a substantial amount of money to me. I have my desired future, but at what cost? In conclusion, Temporal-Subjection theory, TST, redefines time as a subjective and multifaceted experience, deeply intertwined with human consciousness. Time is not a singular, linear progression, but rather a multi-dimensional construct through which consciousness moves, navigating an infinite number of potential futures and pasts. Through a synthesis of cognitive science, quantum mechanics, and metaphysical ideas, TST suggests that time is fluid, malleable, and ultimately shaped by the mind. If time is infinite, then so are the consequences of your choices. Every action echoes across an infinite landscape of potential realities. Responsibility isn't just for today. It stretches across the fabric of time, touching countless versions of you. Clovis.